and I'm glad to see that we maintained the stream of people, and I hope some of the people who are attending the summer school and refresher course have also joined this colloquium. It's a pleasure to welcome Francoise Combs today for the colloquium. Just a very short introduction. Francoise, of course, is absolutely world-renowned astrophysicist working in various aspects of galaxies, galaxy dynamics, and galaxies, the interstellar medium. Particularly in recent years, she is the go-to person for the study of molecular gas in galaxies, using some of the greatest facilities that we have in looking at molecular gas, and she's going to talk about quite a lot of these today, and IRAM, and then NOEMA, and ALMA, and things like that. She did her a PhD from Paris Diderot University. Of course, she studied in École Normale, and then she now is a professor at the Collège de France in Paris, and also a professor at the Observatory de Paris. And then she also has been working in various worldwide collaborations to do with so many aspects of galaxies, and we'll touch on a few today on her talk in the active galactic nuclei, fueling and feedback. She's won many awards recently, of course, the Jules Janssen Prize and of course the Lise Meitner Award, and you can see some of those award lectures on the web as well. Without much ado, I will welcome Francoise to our IUCAA weekly colloquium.
Well, thank you very much, Samak. I'm very pleased to make this talk today. And I will talk about active galactic nuclei, as you see in this first slide. And in particular, I want to address fueling and feedback with recent results that we have with ALMA. So first, to put the scene on, I want to say that we have a paradigm, which is a little change. You know, this paradigm of unification of AGN, that you have AGN of type 1, which are seen almost face-on, and AGN of type 2, which are seen edge-on and which are obscured, and you don't see the accretion disk. In fact, you can see here in a review by Honig recently that it's not exactly like that. When you look at the dust in the mid-infrared, and instead of seeing the dusty torus that we are expecting, in fact, we are seeing a cone. In fact, a cone perpendicular to the accretion disk. Here you have the black hole, the accretion disk here, and the sublimation of dust. And you have this polar cone with outflowing material. But of course, you have still a disk of accretion, and at a parsec scale, you have this maser of H2O, and you have these molecules that I will talk about. So the outline of my talk will be first how these AGN are feeding, how the gas is fueling this AGN, angular momentum, AM problems, and also second, the feedback, because at the same time they are eating some gas, they are also ejecting some gas in jets and winds. And I will make also some point about the molecular tori that you have observed with ALMA recently. And I will just emphasize that they are not exactly at the same orientation as the galaxy. So first, I want to recall the basis of the angular momentum exchange. In fact, you have a galaxy. If it is axisymmetric, you will have only radial forces, and you need, in fact, tangential force to have a torque and bring the gas to the center. And these tangential forces are due to bars, and I just draw here a bar. And we know for a long time that orbits of stars in the bar are parallel to the bar, which is here horizontal. And then at each resonance, from the bar to the particles, they are rotating by 90 degrees. So when this is a 90 degrees turn sharply for the stars, which are collisionless, but for the gas, which are colliding, dissipative, the cloud collisions make the gas turn around progressively by 90 degrees, and you see a spiral. And when the gas is in resonance with the stars, you see these rings that you see at the top right here, at inner and blood resonance, co-rotation, and so on. And to see where are the resonances, you have to plot these curves. What are these curves? Omega is the rotation curve. In fact, what you measure when you measure the rotational field of a galaxy. It's the rotational velocity, v rot, and omega is v rot over r. So this is a measured quantity. Omega is the rate of rotation of the galaxy as a function of radius. And here you see omega minus kappa over 2 and omega plus kappa over 2, which are the kappa is the epicyclic frequency, which is also a derivative of omega, a derivative second order. So all these curves are observed quantities. And what we can see is that when you have a pattern, a bar, which rotating with a constant omega p here, then it encounters these curves with certain points here. And here are the resonances where omega p equal exactly omega, you have the co-rotation. And when you have encounters here, you have the inner Lindblad resonance and outer Lindblad resonance. And when there is a bar in the outer parts, and when you have two ILR, you know that the orbits will be perpendicular inside the two ILR because they change 90 degrees at each resonance, and then they will weaken the bar. So you will not have anymore the primary bar, but you will have an embedded structure, a nuclear bar. And you see in this simulation here, the stars and the gas, the primary bar and perpendicular bar. And in the gas also, you have the perpendicular bar here in the nucleus. So this is very important, these nuclear bars, because they will prolong the action of the main bar towards the AGN, toward the center of the galaxy. And now, I just want to sketch here the action of the gravity torques of the bar. Here you have a bar which is horizontal, and it divides the plane in 4 quadrants. You see here that the tangential force will be restoring all the matter towards the potential well, which is in the bar, horizontal. So the orientation in the pink quadrants will be positive with respect to the omega, the rotation of the galaxy, positive. So all the matter outside the co-rotation will be driven outwards in the outer resonant ring, outer Lindblad resonance here. And when you look inside the bar now, in the right panel, you prolong the spiral structure here in the dust lane, which are along the bar. And then you see that the spiral, so most of the gas, is now in the blue quadrants here, where the torques are negative because the force are still restoring to the potential well. So you have negative torque, and then all the gas from co-rotation to the center, they will go inside and maybe fueling the AGN, unless they are stopped at the ILR, which is the inner resonance. And we wanted to quantify this. And it is possible to quantify. When you have a galaxy, which is a spiral galaxy in a plane, you can deproject it. You compute the potential by the stars. You have the red image, which are most of the stars. Inside, you have not a large influence of dark matter because all spiral galaxies are baryon dominated in the center. So you have mostly the stars, and then you can compute the forces. And here you have an example in a given galaxy, 3627, where you have the 4 quadrants, the bar here and the positive quadrant here and the negative in blue. And then you can put the contours of the gas which is obtained by the millimeter telescope here. And you know that you see here that the gas is in the blue quadrants, so it is subject to negative torques. And indeed, if you average out over radii, you can plot this kind of plot of the angular momentum exchange, dl over L in relative quantity in one rotation as a function of radius. So you see you are inside the 1 kiloparsec in the center. And here we have measured that the torque is indeed negative, and you lose 30% of the angular momentum of the gas in one rotation. That is, in 3 rotations, all the gas will be in the center, fueling the AGN. So you know when the nuclear bar or bar is able to fuel the AGN. So in this frame, we have observed about 20 galaxies with Santiago Garcia Murillo. With low resolution, first it was with the IRAM interferometer, which is now called NOEMA. And out of these 20 galaxies, only 1/3 were observed with a negative torque, that is fueling, smoking gun evidence of fueling. And the others, in fact, they are stalled. The gas is stalled in the ILR for a while, and they were waiting for a nuclear bar to develop inside the ring just to fuel the center. So finally, we concluded that the feeding phase is very short, few 10 million years maybe, and you see the galaxy in a fueling phase only 1/3 of the time. And for instance, an example of a stalling galaxy is here, where you have the dust lane there, and here you have a hole inside the ILR, and the AGN is not fueled, at least at the present state. Now, with ALMA, we can go further in to see exactly when the AGN is at this moment fueled. And this was one of the first galaxies observed with ALMA. It is 1433. It's a prototypical Bard galaxy. You see here the dust lanes. You have a ring seen in HST. It's a blue ring. The blue here is HST. It's a star-forming ring at the ILR. All the gas is inside. And what we discovered with ALMA is this, which is the orange map here. And we discovered that was a second ring inside, which certainly is a second ILR, second inner limb blood resonance. And the gas is still stalled at the second ring. In fact, it's not yet fueling. And finally, we also saw in the minor axis of the galaxy that there was an outflow. So when you compute the torques, and we did this with a 4 quadrants diagram here, you have the bar in this direction, you have the green is a negative quadrant and the positive here in the red, and you see that inside the big ring, you have the second ring at 200 parsec, and when you compute the torque here as a function of radius, you see that indeed it is a positive and a negative only here, but here you have the outflow. So finally, the AGN is not fueled, but there is a storing of gas in the ILR. The second galaxy, in fact, was much more interesting. It was 1566, a Bard galaxy with a spiral. And what we are observing with ALMA is only the center, which is a field of view of 18 arcsecond in CO322. So it's very, very small zoom in the center. And what we have seen, and we are surprised to see, is inside the ring is just at the outer parts of the fold, the field of view. We see that there is a nuclear spiral, and the nuclear spiral is trailing. And this was the main point, trailing, meaning that the torques have some sense and the right sense to fuel the nucleus. Here you see the velocity field, which is rather regular. And I can explain why we are surprised, in fact. I just explained a moment ago that the stellar periodic orbits in a bar are either parallel to the bar or perpendicular. And when you are at co-rotation, they just make no turn here. And when you have a gas, instead of rotating suddenly by 90 degrees, you are following this spiral, 90 degrees gradually. And when you have no black hole, you have this curve, the rotation curve here, omega, and omega minus kappa over 2, which is a precessing rate of the orbits. And in general, you expect that it is the trailing and then leading. When you change the sense of precession, you change also the sense of winding of the spiral. So when you are in this place here, you should have a leading spiral. You see the winding sense is different from the large trailing sense. But here we are very close to the center, and we see the influence of the black hole, the gravitational influence of the black hole, and the curve is going up again due to the black hole. And then what happens is that, again, the precessing rate is increasing, and then you have a trailing spiral. And with this trailing spiral, the exchange of angular momentum is reversed again, and you can fuel the black hole. And that's exactly what we see when we compute the torque here. You see, again, the 4 quadrants, here the negative in blue and the positive in red. And all this trailing spiral structure that you see now deprojected on the plane of the sky is in the negative torque zone. So when you compute the dl over L, you see that indeed it's negative. It's very negative, it's 50%. So in 2 rotations, all these gas will go to the center, spiraling in and fueling the black hole. So the black hole in itself, it makes the curves so that it is fueled. It's a retroaction, a feedback. And this spectacular nuclear trailing spiral We have seen in several galaxies, like NGC 613, 1808 also, that you see a neat, it is a 50 parsec scale here, a neat trailing spiral. We see it in CO322. We see it also in HCN. You see it in HCO+. And the beam here with ALMA was 0.08 arcsecond. So it's even better than HST, 4 parsec. And you can see in the curves here that you are inside the sphere of influence of the black hole, which is 20 parsec. In this galaxy, for instance, people have not seen the before. It was observed with ALMA, but with lower resolution, and people have seen the ring, but in the center, they have not been able to see this spiral, nuclear spiral, which is trailing because of lack of resolution. So you need to go below 0.1 arcsecond to see this kind of structure. Again, for 613, you see here the inner limb-blood resonance and the dust layer. Here, it's inside a 100 parsec scale. You see here the trailing, nuclear trailing spiral, the velocity field, and you see here that you have 5 arcsecond. This right panel is a zoom by a factor 10. You see 0.5 arcsecond here. And now you see in the contour, this trailing spiral that you see here. And in the center is a continuum, which is the AGN, like the synchrotron from the AGN. But at this scale, you see the HCO plus disk, which is completely decoupled. And I want to emphasize that here you find the velocity field is from east to west, and here is north-south. So the inclination and the rotation axis is different from this molecular nuclear disk. That's why we call it molecular torus, because it's a circumnuclear disk, but which is kinematically decoupled. And when you compute the torques again, you have this nuclear spiral structure here. And when you are in this nuclear spiral, you have a negative torque, which confirms that you are fueling the AGN exactly due to this torque. But of course, you still have some positive torques here to store the gas in the ILR. So there are both some gas which is stored there and some gas which is fueling the AGN. We have both. And now for the feedback. In the same time, you have the fueling and the feedback also. In the same galaxy, NGC 613, we have seen an outflow. When you look at the PV diagram, the major axis and the velocity here, you see a very, very steep velocity gradient in the center. And this is the outflow, 300 kilometers per second. This is the rotation, and this is the outflow. You see it's completely visible. And it corresponds to what you see here in a gray. You see the contours of the VLA, so the centimeter plasma jet synchrotron emission. And the outflow is barely resolved in molecules. You see in blue, the blue wing, and in red, the red wing. It has the same orientation as the radio jet, but it is on the minor axis and making an outflow. So on one side, the galaxy is accreting some gas, and the other side, it rejected. In 1808, we see that the gas is fueling the center, the black hole, but there is no, at a small scale, there is no outflow. You see the minor axis and major axis, you don't see this velocity gradient. There is an outflow in this galaxy, but at large scale, at 100 parsec scale, and we think that it is only due to the starburst. In these galaxies, there is a lot of star formation, and the supernovae feedback is making the outflow at large scale. But in a small scale, there is no outflow coming from the AGN. Now, what are the mechanisms to make this outflow from the AGN? In fact, you have two kinds of modes to make the AGN feedback in the form of outflow. You have the quasar mode and the radio mode. Quasar mode means that it is radiative. That is only for AGN which are very powerful, which accrete a lot of gas, Eddington rate or a little below. And when you are at Eddington rate, the radiative pressure, the radiation pressure can push the gas, and you have a wind of gas that is outflowing out of the galaxy. So it is a radiative wind. But what we have observed in the slides before, what a very low luminosity AGN. So it's more the radio mode, we think. And when you have a luminosity which is below 1/100th of the Eddington luminosity, that is, you are not accreting a lot of mass, then you have a radiatively inefficient flow, what we call an ADAF. And the only way to push molecular gas is through radiojets. And indeed, radiojets are not very frequent. They are maybe in 10% of AGN, but still they occur when you have a low luminosity AGN. And it is the only way, when you have no wind, you have no this radiative pressure, to push the gas. And we think that we are observing exactly this mode, the kinetic mode or radio mode. For instance, in 1068, which is a prototype of Cepheid-2, we know that there is a galaxy which is almost face-on, more face-on, but it is a Cepheid-2, so you have obscuring, a disk which is obscuring the AGN, and we were expecting a dusty torus. In fact, we have a molecular torus, and here you see we have also an outflow. The outflow is not perpendicular to the disk. Here you have the disk edge-on, the galaxy of 1068, and of course the molecular torus is almost edge-on with respect to the galaxy, and then you can have a feedback which is entraining some molecular gas, so molecular outflow, and also a jet, radio jet. And this is also seen recently with ALMA. You see the gas which is really in a thin molecular torus in CO221 here. It is really in the zoom of this region. Here it's the inner ring of the inner in-band resonance. Here you have this zoom. And here we are surprised in CO625 to see the dust emission in continuum, which is not aligned with the molecules, but is more in the polar ring, again, the polar direction, which means that, again, it's like in the mid-infrared interferometry, you see the polar dust. And when you look at the sphere, the very neat result by sphere by Grotado et al., what you see here is the mid-infrared, but in polarization. So it's more easy to see what is exactly the polar structure. Here you have the molecular torus and the polar ejection, and the dust is in the polar cone here. It's very nice, and it corresponds exactly to what we see in ALMA, here the contours, which is perpendicular and molecular torus, which has not the same orientation as the main galaxy. And this is frequently seen, well, frequently out of 149 AGN, you have 21 which show in the mid-infrared interferometry perpendicular to the accretion disk, like 1068. Now, we have also jets, molecular jets, which are very, very collimated. And this one is an example of these, which is a mystery because we don't see the radio jet, we don't see the plasma. We see here with Susan Alto et al. Here with ALMA, what we see here is a CO322 emission. In gray, you see the emission at V equals 0, systemic velocity, and the wings of the emission, the blue wings and the red wings, are seen here in contours, and you see that are forming like a jet. In the dispersion also, you see this clearly, and when you go to higher resolution, you see it's very, very thin, and this is collimated. It cannot be by a wind. Maybe the gray thing is a wind by a cone or something else, but here you have certainly a jet. But we don't see it's a very radio quiet galaxy. We see with the VLA the core, but we don't see the jet. So maybe we have to look back with the VLA with higher sensitivity. But for the moment, we see the molecular jet, but we don't see the radio jet. But at least we think that there is one. And what is the peculiarity of this jet also is that you see here it's blue and red, but it changed sign. It is red and blue here. So we see that the jet is almost in the plane of the sky, and it's sufficient that it is precessing by 10 degrees to be towards you, to recessing away from you. So we think that it is a precessing jet. And why it is certainly driven by the radio jet, because the collimation is due to the magnetic field, which is confining the radio jet. It cannot confine the molecules, so the molecules may be entrained by the radio jet. And we see this kind of precession, like a micro quasar, like in a galaxy, you have a binary which has a black hole, a very small black hole, stellar black hole with a binary. And then you see that you have this kind of precession. So when we make a model of the precession, it fits the observation. Here's a model and the observations. We think that indeed we have an outflow, which is precessing by 10 degrees in the plane of the sky. Of course, you can have the jet and also some wind ejection, but both the mechanism can apply also in the same sense. Now I want to emphasize the molecular tori. And again, I come back to this 613, where we see not only at the large scale, 100 parsec scale, you see some orientation, but at some very, very small scale, here is 10 parsec scale, you see that the rotation, the kinematics is completely different. And we call it the molecular torus because it's a different component, decoupled component. And this we see in many galaxies. In fact, we have observed now a dozen, but here you see 1326. There is a small ring here. Again, it is almost face on, but here is a John. Again, it is a very small torus around the galaxy. 1365 also, it's inside this bar galaxy, and we see at 10 parsec scale, we see a torus, more face on this time. And out of the 8 galaxies observed in this paper, for instance, 7 out of 8 had a torus, a decoupled molecular circumnuclear disk. And you see the radius, typical radius is 10 to 20 parsec. The H2 mass of this molecular torus is about 10 to the 7 solar mass. And what I want to emphasize is the inclination of the torus, which is different from the inclination of the galaxy. You see, it has a random inclination as if it was precessing. So what are the mechanisms of this precession? Why is it unaligned? In fact, there are several mechanisms. I will describe one or two. First, there is a radiation-driven warping instability, like Pringle in 1996 has discovered. And the principle is well seen in this simulation by Maloney and Begelman, for instance, in 1997. You have a disk, a recursion disk, which is optically thick to the radiation of the center, of the quasar here. So once it receives a photon, it will absorb completely, and then it will re-radiate. If it absorbs, it comes from the center, so there is no momentum. But if it is re-radiated, it will radiate like this, perpendicular to the surface, and it will have a momentum. So you can have a torque. So this torque will amplify this warping of the disk, and this simulation explains how you can have this warping instability only due to radiative pressure. This is one mechanism. Another one is magnetic instability, but when you look at the comparison with observation, it is a little contrived, so I will not speak more about that. And the third one, which might be more compatible with observation, is a relativistic effect, the Bardeen-Petterson effect, which is due to the frame dragging effect or lens stirring effect, that the black hole in general is spinning most of the time, and we think that in the center, the supermassive black hole of galaxies are spinning. They are the result of many merging of black holes. And then when a gas arrives to accrete on the black hole, it has a different orientation than the black hole spin. And the black hole spin entrain in this frame dragging, entrain the gas, and it will try to align the gas around the black hole, but the rest is not at the same orientation, so there will be a torque. And this warping, which is always there, in fact, it depends also on the viscosity. If you have a highly viscous gas, for instance, the diffusion regime where alpha, the famous alpha viscosity parameter of the Chakra-Shunyaev, when it is very large, then all the gas is entraining itself in a warp like this picture, for instance. And when the viscosity is not enough, you can have a breaking of this warp in several rings, like you see in this simulation by Neil et al., when you see this gas is breaking in several rings. And of course, the rings are differentially precessing, and they will collide, and then they will fuel the center. So it's a way to fuel even better. So this Bardeen-Petterson effect has been seen, in fact, in the maser. You see, for instance, the 4258 well-known maser in H2O. These maser are coherent emissions, so they are very strong. You can do that with VLBI, like you see the emission here. And then you can have a high spatial resolution, and it has been simulated by Martin et al., this warp of the observation of the points, and the warp, due to the Bardeen-Petterson effect, is very compatible with what is observed. Also in NGC 1068, there's water masers with the velocities in colors, and this is also very well compatible with this. It was simulated by Caproni et al. You see here the schematic view of the simulation, and he's simulating the warps in the H2O maser, and also the precessing rate of the jet, which is corresponding to this precession. And it gives some figures, which is very interesting to see. The alignment time scale to align the rings around the black hole in the accretion disk is about 7,000 years, so very short. Of course, we are very close to the black hole. And all this warping and precession can last until 1 parsec for a supermassive black hole typical of this low luminosity AGN. And the velocity of the jet was 0.2 times the velocity of light. So this works quite well. And this might be the explanation of the precessing of the jet and the warping and the fact that the molecular torus are not aligned with the galaxies that are randomly aligned. Now I want to also exploit this discovery of molecular tori by, for instance, this kind of 1672 galaxy, where you see, again, it is almost face-on galaxy, but the torus is almost end-on. You are inside the sphere of influence of the black hole, and you can also try to estimate the mass of the black hole by the velocity of the gas. And this was done here. You see the PV diagram here. You see it's very gradient of velocity is very high. In 10 parsec, you reach 400 kilometers per second. This is due to the black hole. If you make a model of the rotation curve, it is like this, with only the stars and all the mass which is in the disk. But when you plot a black hole here, in addition, you see this peak is due to the black hole and then the rotation here. So you have typically a black hole of a certain mass, here 5 × 10⁷, to fit this PV diagram. But of course, you can also fit the 2D. Well, I pass about this, and you have the 2D model also. You have the intensity, the velocity, all the moment, the sigma in the observation and in the model. So you have not only the PV diagram in 1D, but you have the 2D, and you can have a good fit of the black hole mass. This was done also in 1365, for instance, the model and the observations. You see how you can model the velocity curve with or without black hole, and you deduce the mass of the black hole. This was also done with the WISDOM project, which is more around early type galaxies, more massive. The black hole is more massive also, and the beam has not to be so small because the sphere of influence of the black hole is bigger. And this was done in several galaxies also. In this one, unfortunately, there's a hole in the molecular gas, but still you're able to measure the mass of the black hole. So after that, you can compile all this, and you see the m sigma relation, so mass of the black hole and the velocity dispersion of the center of the galaxy, which is a proxy for the mass of the galaxy or the mass of the bulge. And you see that we have a very nice relation, meaning that the mass of the black hole is always a given percentage, maybe 0.2, 0.5% of the mass of the bulge of the galaxy. But of course, when you look at the low mass end of this relation, it's less defined. For the early type galaxies, it are the blue points defined by ALMA, and for the late types is the red points. It's still a lot of scatter, and we hope to reduce the scatter by the measurement of the CO gas, the molecular gas, which is a new tool with ALMA to determine the mass of the black hole. Now I come back to this non-alignment that I have emphasized, that indeed each time we see the molecular torus, it is different orientation than the main galaxy disk. It is not new. We knew, for instance, in NGC 4258, there is in pink here the normal disk of the normal spiral, and in blue you see both the jet. It's not spiral arms, it's a jet which is bent by interaction with the disk of the galaxy. We see that in the radio jet, and we see that in the X-ray also. So you see that the jet is in the plane of the galaxy, which is very surprising, but it is due to the fact that the accretion disk is not aligned with the main disk of the galaxy, and the jet is coming perpendicular to the accretion disk. So you have a way to have the orientation of the accretion disk. And you see that there is a lot of feedback, especially because of this misalignment. You can have more feedback of the AGN to the disk of the galaxy, more coupling. In the Milky Way is the same. You have, normally you see the Milky Way edge-on because we are inside the Milky Way. But when you look at the center of the Milky Way, you see this ring in molecule, we see HCN in orange, and you see this mini spiral in green, which is ionized gas, seen with a VLA in the jet. And it looks more face-on than the edge-on of the galaxy. So again, it is misaligned, and it's also off-centered. And to explain that, we have made a simulation of Milky Way type galaxy with a gas, star formation, and so on. You see a bar here, several snapshots, and after some time, the gas is unstable to star formation. So you see this very turbulent gas making some stars. And of course, there is supernovae feedback. And all this supernovae feedback is sending a lot of gas in the halo, which is not escaping, of course, because it has a low velocity, but it is coming down to the plane of the galaxy like a fountain effect. And this fountain effect means that the gas will come down with NA orientation, in fact. It is not accreting in the plane of the galaxy, but at some orientation. And in this particular simulation, it was coming back perpendicular. It was rather stable because when you have a polar ring, a polar structure, it is more stable than when it is precessing differentially in some orientation. So you see here the face-on view of this galaxy and the edge-on view. And in edge-on view, you see that you have a lot of gas that have come back, which is perpendicular, making the spiral in the polar plane. And this can explain why you have a lot of gas, which is not in the plane of the galaxy, but coming, accreting with NA orientation. So we expect to have this, this misalignment, in fact. So the first part I will summarize here. I've explained you why we can explain fueling in the galaxy, in the bar and nuclear bar, and especially nuclear spiral, because we have seen in several cases with ALMA that at 10 parsec, we have a nuclear bar and nuclear spiral, and you can fuel. So at least we are seeing the smoking gun evidence of fueling. We have seen also a lot of feedback, and in molecular outflows, sometimes they are very, very collimated. Even if we don't see the radio jet, we think that it is a radio mode which is doing that. And I emphasize that we have seen a lot of molecular tori. That is, it's not dusty torus, it's molecular torus, which is about 10-20 parsec scale. And it is completely different orientation, decoupled kinematically from the rest of the disk. That's why we can identify a new component. And maybe this precessing that we see in some cases is due to the Bardeen-Petterson effect. Okay, so in the minutes that are remaining, I will want to speak about a related topic that we are also collaborating with Professor Somak Reshogiri, our chairman here, which is the group dominant early time galaxies. And you see here that we have observed about 50 galaxies, the center of galaxy of groups. And one of the idea behind this, this project was to know if we can extrapolate what we know in clusters, where you see that there is cooling flows from the hot gas, the X-ray observed gas in clusters. They're cooling and fueling the AGN in the center of the cluster and making some feedback and so on. So this is the prolongation of this working group. So in each of these groups, which are seen in X-rays, so it's in between the small groups like the local group or the big clusters, you have groups which are rich enough to have X-rays emission, so hot gas. And in the center, you have early type galaxies. So normally, early type galaxies have no molecular gas, but here we have search for molecular gas. You see here in green the beam size where we have observed the molecular gas, either with IRAM or with APEX, even in the south. And in fact, we have surprisingly observed in half of them, we have observed molecular gas. So these galaxies are passive, they are early types. And when you look at the main sequence of galaxies, so star formation rate as a function of stellar mass, all these galaxies are below the main sequence. We call the main sequence those who are aligned on the gray lane here. That is, star formation rate is proportional to this mass of stars, and they are forming stars regularly with a depletion time for their mass of gas, which is 2 gigayear with normal galaxies. But here, all these galaxies are below, and we knew that because they are early type galaxies, elliptical galaxies, that are quenched, in fact, of their gas. But still, in these galaxies, we are able to find molecular gas. So you see here a relation linking the molecular gas to the star formation rate, and they are all aligned on the what we call the Kennicotte-Schmidt relation, which is the proportionality between the fuel and the formation of stars. And the line here means that they are depleting their gas in about 1 or 2 gigayear, like the others. So finally, they are relatively normal, which is also a surprise, because they are passive. They have a small amount of gas, but they are consuming their gas as the others are doing. So this is very interesting. And we are trying also to see if there are environment effects. You see here the molecular gas detection as a function of richness of the group. We have not enough statistics here for the rich group, but for the small richness, we find 50% of detection. And we try to find correlation with the X-ray content of the group or with the power of the radio emission, but there was no correlation. And at the end, we were interested to know what is the origin of this gas. So indeed, there is some cooling flows at the origin of this gas. We have, for instance, the galaxy NGC 5044, which is the center of a small group. You see in red here in pink, the H-alpha filaments. And in blue and red, you find the clumps that we have seen with ALMA, which are following the filaments with some velocity. Some is also absorbing in the center. But it looks like what's happening in clusters with filaments of cooling gas to fuel the center. So we have this kind of cooling flow, but we have also other origin for the gas. We have a merger, for instance, like 7252, two galaxies merging, so bringing some gas to the center, or also interactions like the group of NGC 128. And we see that there is interaction between the companion 127 and so on. So accretion of gas from companion galaxies is also one mechanism to explain the presence of gas in these early type galaxies. So at least we are continuing this project to know what is happening in groups while we know better what's happening in clusters. So thank you very much, and you can ask any question. Thank you.
Thank you very much, Francoise. That was absolutely fascinating talk on what molecular gas can tell us about in galaxies, in groups, in clusters, and linking between various effects of outflow and inflow to the effects we see in the interaction of the galaxies and the groups and clusters. I would, and thank you for keeping in time. I would like to now the audience to ask questions, and the way to ask questions is the following. There is a provision to raise your hand. If you go to the participants window at the bottom, you can see how you can raise your hand, and I will unmute you in the sequence of you asking the question. And so I already have Kanak Saha, who I expected to be the first person to ask the question. Kanak, you're unmuted. Go ahead and ask your question.
Hi, Francoise.
Hello, Kanak.
Right. So I wanted to ask a question where in an image, you showed NGC 1808, where you show the nucleus spiral.
1808.
Yeah, it's very early, like that.
Little more. Little more. Little more. Yes, maybe here.
No, a bit before this.
1808. Ah, yes, the small. Yes.
Yes, the small nucleus spiral.
Yes, here.
Exactly like.
Okay.
I see that this is not at the center. This is a bit off-centered.
No, it is at the well. Sometimes it is not at the center, but here we have taken the NED. You know, the NED center, which is not at the center. You know, there was in precision when you are going to 0.04 arcsecond.
Okay.
The NED has not the right center. So when we measured with ALMA the position of the continuum in synchrotron, it was always at the center of the nuclear spiral. So we are here at high precision. So the NED was not giving us the right center.
Okay, I see. That explains it. Because I thought this is off-centered. So
no, this one is the continuum in ALMA is in the center of this.
Okay, I see. Okay, thank you.
But it's true when you are talking about off-centering, it's true that 1068, for instance, it is off-center. The AGN is not at the center of the big ring of the ILR ring, inner in-band resonance ring. So you have a wandering of the black hole with respect to the ILR, but not with respect to the nuclear spiral.
Francois, what does this mean? I mean, what is the off-center in the cases where it is off-center?
1068, I can show you 1068 maybe.
So what does it indicate in terms of what's happening in the center?
And I think, yes, if I can find it, yes, here, I think you see here, the AGN here is not at the center of this. But there is an M equal 1. It's very small, but still it's, and we make a cartoon here, but the AGN is not at the center of the ring. Because, in fact, there is an M equal 1, it's lopsided. There is a mode which is making this lopsidedness, and this is a wave, in fact. So it's not going far, it's just making some waving wandering here. But for 1068, it's very clear. The AGN is here, not at the center.
Are there any other questions? I don't see any other hands up. Please look for the hands up button in the participants window and please ask a question. While we are waiting for that, can I, Francoise, ask you one question? And that is, you have quite a sample of these systems now in which you can see the inflow and the outflow right in the middle around the supermassive black hole. And you can link it directly to the AGN phenomenon that's happening. You see also more information in there than you see in, say, normal radio maps. So does it give you a better insight into the, say, the duty cycle of AGN activity, in particularly the low mass galaxies?
Yes. In fact, when we have more statistics, it will be better. But already now, we know that it is a small duty cycle. That is, the fueling is about 30%. It's not fueling every time. So we have some intermittent accretion of gas, and it is 30% about. But we will have more precise figures afterwards when we have more data, where we have plenty of consortium of ALMA observation of nucleus, like GATOS. We have a NUGA, we have masters and CARS. So a lot of groups are doing that. And each group is doing 20 objects. So after some time, we'll have 100 objects of this, and we can give a figure which is more precise.
And is there any hint of a difference, a systematic difference between, say, very high mass galaxies and lower mass galaxies in getting duty cycle?
Yes. We think that here we are speaking of the radio mode, and when you have quasars, we have more the wind mode. So we don't need any radio jet. It's more frequent, in fact, because radio jet is rare. So once you have a lot of accretion, then you have a wind, and it's more frequent to have this feedback.
Before going to Indulekha's question, can I ask Kanak, is your hand up? Do you want another question, or I haven't just lowered your hand yet? Kanak, do you have another question? Otherwise, I'll go to Indulekha. Okay, great. Dr. Indulekha unmuted you. Indulekha's question.
Professor Combs, nice talk. I just want to know, there are these papers on the IMF in elliptical galaxies being bottom heavy. Now these elliptical galaxies are falling off the Kennigan-Schmidt relation. Is there any relation in these galaxies falling off the Kennigan-Schmidt relation?
We found, yes, at the end, I mean, we found some, not in this group dominant elliptical galaxies. There are some elliptical galaxies that are outside, but it is not in these circumstances. We found, for instance, in jet-induced formation, for instance, in Centaurus A, when you have star formation in the jets, because it's induced by the jet, and it is outside the Kennigan-Schmidt relation because it's outside the disk. When you are in a disk, in general, you are in the Kennigan-Schmidt relation. You have exception when you are outside the disk. You go far away from the disk, or you go in the jet, or when you go, for instance, in the room pressure tails of galaxies, on tidal tails. Each time you are outside disks, you get out of the Kennigan-Schmidt relation. But when you are in the disk, you are still in the, and we think that it is due to the pressure of the disk. When you have a disk of stars, and in these galaxies, there are early types, but still there is some disk. You know, there are elliptical galaxy with some disk. And when you have a pressure due to the stars, then you have the star formation exactly as in spiral galaxies. Even if you have less molecular gas, you have less star formation, but the law is the same.
Thank you very much. Is there anybody else who wants to ask another question?
Can I ask a question, Sean?
Yeah. Before going to Pranav, can Kandu ask your question? Yes.
Yeah, I was intrigued by the fact that you are saying that you saw molecular outflow, but you are associating it with some radio outflow. Although it was radio quiet. What was the evidence for that?
Oh, you are thinking of 1377.
Yeah, that in the beginning you saw.
Yes, if I can go back. We see, yes, we see the evidence is that, yes, here. Okay, so we see here that there is a very, very, very collimated molecular jet. We don't see any radio jet, but we don't know how you can collimate a molecular jet.
Oh, okay, fine.
That's the problem, is that because in general you have a magnetic field and you have to have a couple to combine and to confine the ionized gas to the jet by the magnetic field. But if it is only molecular, how can you make this very thin without a jet? That's the problem.
Good, thank you. Yes, I agree. I have just one more, if Shamak.
Yes, please go ahead. There aren't any other questions up. Yes.
I was wondering that you were showing all these barred galaxies feeding the nucleus, but surely this must be happening in normal non-barred spirals also, right? So is it that you have not seen them, or you are not showing them, or what?
You mean there was a bar? Yes. If I can go back.
In the example that you showed, there was a bar.
Yes, there was a bar. Yeah.
Bar.
There is always a bar and a ring also. And inside the ring, there's a nuclear bar and a spiral, nuclear spiral. Each time you have a bar. It's not strong in each case. Sometimes it's oval, sometimes it's a weak bar, but there is always a bar. Yes. All these galaxies are barred.
Even when you see normal spiral galaxy, you think there will always be...
But in spiral galaxy without bar, it is possible too, because these talks happen also in spiral. They are stronger in bar, but in spiral, yes, it's also a density wave. Yes. And you have talks also with spirals. Yes.
Right. Okay, thank you.
Thanks very much. Let's unmute Pranav Limai, who has a question.
Hello, ma'am.
Hello, go ahead.
Yeah.
Hello.
My question is a bit off track. There's a famous anomaly for the Vela pulsar that some people think that it's accreting matter similar to a quasar and the particle beams are radiated across its rotation axis, while the other people think that it's just the projection effect of due to which the magnetic and rotation axes are seem to be aligned. What are your views on this debate?
But that's nothing to do with the talk today. I mean, I'm sorry, this is quite irrelevant to today's talk. Do you want to take this question? I think let's take.
Quite understood. It is magnetic.
Yeah. So let's stick to today's topic, because you've asked a question that is not covered by today's talk at all. Thank you. Anybody else? Anybody else has any questions? Great. If there aren't any more questions, well, thanks to the speaker for a wonderful talk. And thank you for making time in the middle of your day. We have a provision of applause on Zoom if you go to the applause button in the participant window. But in any case, we have a silent applause greeting you today, Francoise. Thank you very much for it.
Thank you very much. Thank you.